Hey guys, so starting from today, I'm going to be doing something a bit new. So I'm going to be doing problems of the day, and the main purpose for these is not really to teach anything. I guess it's more for my own personal enjoyment. So yeah. So without further ado, today's problem of the day will be a momentum problem, and it comes in two parts. So part A says you sit on a crate at rest on frictionless ice. The combined mass of you and the crate is m. You hold a block also of mass m and throw it horizontally so that the relative speed between you and it is v naught. What is your resulting speed? So if I draw it out, so basically I'm on frictionless ice and I'm on this crate and our combined mass is m, and I threw a block horizontally and it also has mass m. And I'm going to say that the speed of the block is v1 and the speed of me in the crate is v2. And initially, the system, since it was at rest, I was holding the block, so the system initially looked like this. And because the surface of the ice is frictionless, we know that the horizontal momentum must have been conserved, so it has to be zero, or it's always zero. And it also said that the relative speed of the block I threw is v naught. And what it means by relative speed is, so for instance, if I saw myself as being at rest, so this is me in the crate, and I perceive myself as being stationary or in the stationary reference frame, then obviously it would look like the block I threw is going faster than it really is. And in that case, the problem is saying that the velocity I perceive it to be having, or the speed I perceive it to be having, is v naught. And so an example of real life situation, I guess, is if someone was running this way at 2 meters per second and someone was running this way at 3 meters per second, well, someone in the stationary reference frame would see that this person's going at 2 meters per second to the left, or this person's going at 3 meters per second to the right. But the person here would see the person running to the right as going at 5 meters per second. So that would be their relative speed. So back to the problem. So 2 plus 3 is 5. And similarly in the problem, we can say then that V1 plus V2 is equal to V naught. And also, as I said earlier in the problem, the momentum of the system consisting of the block, me, and the crate has to be 0. So then, since we have that m times V1 has to be equal to m times V2, because they're going in opposite directions, then the momentum of those two has to cancel out to be 0. So we have mv1 equal to mv2, which means that v2 is just equal to v1. And from this we can see then that 2v1 is v naught because we're plugging it back into the initial equation. So now our speed, which I call this v1, is equal to v naught over 2. So yeah, that was pretty straightforward. And part B is going to be a bit tricky. So now for part B, it says, now assume that you cut the block in half and throw one half, and then wait a moment and throw the other half. What is your resulting speed? Assume that whenever you throw something, the relative speed between you and it is v naught. So for this one, I guess I'm going to break it into 2 stages. Well, actually 3 stages. So for the first stage, I'm at rest. And well, the whole system is at rest. And this system has a mass of 2m and it consists of me, the crate, and the block, which has mass M. So this is going to be when I'm at rest. And then this next stage is going to be, I'll just say it's the first throw. So now that I threw one half of the block, so the mass of the system would be, or not the system, the mass of me, the crate, and half the block is 3 halves M. And then half the block has that mass of M over 2. And I'll say that its speed is V2, and the speed this way is V1. And the problem said that the relative speed whenever you throw something is V0. So just like in the first problem, we can say that V1 plus V2 is equal to V0. Actually, I'll just change the color of this to make it a bit less confusing. So this will be the first half of the block that I threw, and it has speed V2. So yeah, this is the first throw. And then, so once again, the initial momentum is 0. So the momentum here has to also be 0. So these momentums in each of these directions has to cancel out. So we have the 3 halves m times v sub 1 is equal to 1 half m times v sub 2. And now to simplify this, we can multiply both sides by 2 over m. And if we do this, we get that 3v1 is equal to v2. Now if we plug it into this initial equation, we can see then that 4v1 is equal to v0. So v1 is equal to v0 over 4. And we're not done yet. We just found our speed after our first throw. We still have to take into account the second throw. So for a second throw, now we have mass m, and by we I mean me and crate. And then so the first half of the block that I threw, once again, is just has a mass of m over 2 and has speed of v sub 2, since the ice is frictionless, so it couldn't have slowed down. And then the second block, or second half of the block I threw also has mass m over 2, obviously, since the total mass of the block is just m. And I'll just say it has speed v4. And then I'll just say that the speed of the part of the system would be in the crate is v3. And once again, to conserve momentum, the total momentum of the system still has to be 0. And now, as the problem said, whenever I throw something, the relative speeds between me and the object I threw is v0. So then we have v3 plus v4 is v0. And yeah, so this is the second throw. So v3 plus v4 is v0. And the momentum still has to be 0, so m times v3 is equal to, so this can be written as m plus, I guess, the average between v2 and v4. So from this we can just see that v3 is just v2 plus v4 over 2. And we want to find our final speed in terms of v0. And we said that v1 is v0 over 4, and we also said that v2 is 3v1. then V2 is just 3/4 V naught. And we can plug that back in here, so we have V3 is equal to 3/4 V naught. And also we can also find V4 in terms of V naught. Using this equation, we get that V4 is just V naught minus V3. So now we can add V naught minus V3, and this is over 2. Yeah. And then we want all the V3s on one side, so we can add V3 over 2 to both sides of this equation, and we get that 3V3 over 2 is equal to 21 over 12 V naught over 2. So then we get that 3V3 is equal to 21 over 12 V naught. And if we divide both sides by 3, we get that V3 is equal to 7 V naught over 12. And that is our final answer for our speed after we've thrown the second half of the block. And yeah, so to sum it up, so for part A, we just had to solve our speed after throwing the whole block, and we got that that was just 1/2 of the relative speed of the block we threw. And for part B, we divided it up into 2 different throws. So first we threw 1/2 the block while keeping the other half. And after a while we threw the other half of the block, and we got our final speed to be 7 V naught over 12. So that's it for today's problem of the day. I hope you enjoyed this video, and thank you for watching.